I'd like to welcome all of you to this edition of the Della Pietra Lecture Series. It's made possible by a very generous gift of Stephen and Vincent Della Pietra and their family. So I would like to start by thanking them for making all of this possible. The speaker in this example of the series is William Bialek from Princeton University. He'll be giving 4 talks during his 2 days here. This talk is for a general audience, and his talk at 5:30 tomorrow afternoon is a public talk. And then in between this afternoon and tomorrow morning, he's giving 2 other talks aimed at people with more background subjects. But all of the talks and their titles are listed right outside on the monitors. So if you're interested in some of the other talks, please check that out for the titles. So Bill Bialik is the John Archibald Wheeler / Battelle Professor of Physics at Princeton University. He's also a member of the multidisciplinary Louis Siegler Institute. He's also a visiting presidential professor of physics at the Graduate Center of the City of where he's helping to launch an initiative in theoretical science. He was educated at Berkeley, both as an undergraduate and a graduate student in biophysics, and his research interests have ranged over a wide variety of theoretical problems at the interface of physics and biology. He's best known for contributions to our understanding of coding and computation in the brain. He and his collaborators have shown that aspects of brain function can be described as essentially optimal strategies for adapting to the complex dynamics of the world. Throughout his career, Professor Bialik has been involved both in helping to establish biophysics as a subdiscipline within physics and helping biology to absorb the quantitative intellectual tradition of the physical sciences, and I believe that the themes of all his talks while he's here at Stony Brook. So with that, I'd like to welcome and introduce.
Thanks, John. So in the physics department at Berkeley, at least when I was a student there and sometime after, there was this habit of applauding when colloquium speakers were introduced. And as a student, I didn't know whether that was just a matter of politeness or whether it was because all these people were really important. And of course, the first time I tested this was when I went, for the job interview, right? And I sort of sat there wondering, wonder whether, when they invite sort of kids who are applying for jobs, do they also applaud before they talk? They did. So I conclude they're like you, they're all very polite. So they don't wait to find out how the talk's going to be. So I'd suggested, when we were talking about this visit, which I was really looking forward to, we talked about trying to do some things for a general audience and some things for a more technical audience. And so this is, as John mentioned, one of the things for a general audience. So for those of you who are more expert, I'm not going to apologize, but I would note that in some sense it's not really designed for you. It's designed for the non-experts. One of the things that I think is really fun to try and communicate is the tremendous power of mathematical ideas to unify our understanding of diverse phenomena. And I think that the idea of entropy is often not used as an example. And I'm not really sure why, because it's a fantastic example. Most of you have heard about entropy in the context of the second law of thermodynamics, so you know that the entropy of the world is always increasing. You may know that this has something to do with notions of order and disorder, and the sense that the entropy of the world is increasing is related to it becoming less ordered. Over a period of 100 years, almost precisely, we went from the ideas of the second law of thermodynamics telling us something about what can happen and what can't happen, and sort of being relevant for building steam engines and all sorts of very 19th century things, to this sort of miracle that happens in the middle of the 20th century where all of these ideas of entropy reappear, but now they're describing not steam engines, but the information that we gain when we communicate with each other, and the space that it takes to write things down when we want to store information, and the way in which we can transmit signals to one another without making mistakes, despite the fact that there's all sorts of errors in our environment, and so on. And this is the connection that I want to try and expose for you. So I'm not going to say anything in this lecture that I or my immediate colleagues did. It's all very classical, but I hope still. Well, I hope I can communicate to you why I find some of these things still so remarkable. So let me begin at the beginning. We know that if I have two objects, and one of them is hot, and one of them is cold, then if I let them touch each other, so I don't know, I build a little bridge here, then what happens is that heat flows in this direction. And the consequence of that is that the hot object cools off and the cold object warms up, and eventually this stops when the two objects are at the same temperature. And so you all know this because if I leave this here, the water, which, trust me, started out a little colder than room temperature, will eventually end up at the same temperature as the room. And so that's just this phenomenon. All right? Great, thanks. So heat flows in some directions and not others. And this is also related to the fact that some chemical reactions happen spontaneously and other ones don't. But this is sort of the most elementary version. Now, in the mid-1800s, you could say that what people were trying to do was to do a kind of bookkeeping of these heat flows. And they noticed a problem, which is that although it's perfectly clear that heat flows in some directions and not others, there doesn't seem to be a notion of heat content. So since this is colder than the room, right, it's going to absorb heat from the room. But if I ask you, what is the heat content of this glass of water, that turns out not to be a sensible question. It doesn't have a well-defined answer.
Can you illustrate that?
Yes. You actually, by the time this comes to room temperature, you don't know whether I got it out of the refrigerator and it absorbed heat from the environment, or I took it off the stove and it released heat to the environment. There's no way to tell by looking at the water. There's no. So the technical version is I can talk about sort of changes in heat, right? And okay, there are a few of you in the audience for whom this will make sense, right? So these get called dq for little changes, but there's no function q, right, of which this is the derivative. That's the point. So the technical statement is that there's no function of state that corresponds to heat content. So what people discovered was that, so you can't say that the heat content of objects goes up with time. That doesn't, right? It just doesn't work. And yet there's something orderly going on here. So what people figured out was that there is a quantity such that if I measure temperature in the right units, or on the right scale, then if I take the amount of heat that flows and always divide by the temperature, then this quantity eventually becomes a function of state. So I can actually integrate this thing. So what does that mean? It means that if I try to count how much heat flows in and out of an object and sort of add it up to get the heat content, that doesn't work. If I take different paths to the same state, like my example with the water coming out of the refrigerator or off the stove, I'll get different answers for how much heat went in or out. But if I'm very careful that whenever the heat is flowing, I normalize the heat flow by the temperature of the environment, then I add everything up and it works out right. Okay? And so this quantity is called this sort of, if you want, you sum heat flows normalized by temperature. This quantity was named entropy. And that is, as I say, a function of state. I can ask, what is the entropy of the water in this glass? And that has a well-defined answer. And
Whether you took it out of the refrigerator.
exactly, exactly. So the fact that it's in this state right now, it has a well-defined entropy no matter how it got here.
Now what?
Yeah. Well, you know, not everything is conserved.
Well, it is.
Well, yeah. Not in the glass, but it's open. Good. And so, if you want, in this view, the reason that the entropy of, the statement that the entropy of the world is going up, so, which is the second law of thermodynamics, is now I can go back to this and ask what's going on. Well, heat is flowing out of this object, so that's going to make its entropy go down. But the amount by which it goes down is the amount of heat that flows out divided by its temperature, but its temperature is very high. The entropy of this one is going to go up because the heat's flowing into it, but its temperature is low. So the amount by which the entropy increases over here is bigger than the amount by which the entropy decreases over here. And so the statement that the entropy of the world increases is the statement that the heat flows from hot to cold bodies. Okay. Good. So, so this is seen this way, and some of you may know that this allows you to. This idea that the entropy of the world has to go up, this allows you to ask, for example, if I actually, if I want to build a refrigerator, how much energy do I have to use in order to suck enough heat out to lower the temperature, right, of the object? And so there's a maximum efficiency of refrigerators. There's similarly a maximum efficiency of things that are called heat engines, but nobody sees a heat engine anymore, but we still have refrigerators. We still have heat engines, but they're hidden away somewhere. Power plants. So this was incredibly, this started as a kind of bookkeeping device, but then had all these remarkable consequences about what kinds of things you can do and what kinds of things you can't do. And the laws of thermodynamics, there are 3 of them, of which the third one probably isn't true, even though it says it is in the textbooks. So the first one is the conservation of energy. So this, again, you can think of as a kind of bookkeeping device. You can't get something for nothing, right? In fact,
You'll never get elected to public office for that state.
yes, well, that's true. Right. And right, so the paraphrase is often, the first law is that you can't win, and the second law is that you can't break even, and the third law is you can't get out of the game. So you can't break even here is that since the entropy of the world's always going up, of course, once the heat flows this way, you kind of can't get it back, right? So you're always losing. As long as I have something hot and something cold, I could actually do something useful. I could warm up a drink or cool it down or something like that. But as soon as they end up at the same temperature, I can't really do anything useful anymore. I just have a bunch of stuff. So this increasing entropy of the world is slightly depressing, but true. Now, this is, I don't know, a product of, let's say, roughly 1850. And it really belongs properly to the subject of thermodynamics. And as I say, it has some of its roots in these very practical questions about building heat engines and refrigerators and so on. By 1900, before that, but certainly by 1900, entropy ends up in, sort of reappears in a very different way. And so, well, let's say, leading up to around 1900, we have people like Boltzmann and Gibbs and many others. And this description is completely macroscopic. There are no atoms here. There are no molecules. There's just flows of heat and temperature. And what happens leading up to 1900 is that this view of the world as being made out of atoms and molecules appears, and or reappears. Of course, it dates back to the ancient Greeks. And these guys did something which is really quite remarkable. Remember that one has seen by the 1800s, certainly by the late 1800s, the tremendous triumph of the Newtonian worldview. So, we can calculate the orbits of the planets. We can calculate the times at which eclipses are going to occur. You should always remember, right, that physicists and mathematicians, our original employment was doing things like predicting eclipses for the king so that, they would know when these great omens would occur. So every time you learn that there's going to be an eclipse and you know when it's going to be, you should be reminded that this is how we made our living not so long ago. Now it's sort of commonplace, but it really was quite remarkable. I mean, if you didn't know what was going on and you walk outside and all of a sudden the sun is blotted out, you could be forgiven for thinking that there's some higher power who has decided to smite you. But now we can calculate all this. And we calculate it in a view which is very deterministic and, well, we'd now say mechanical, right? The positions of all the planets obey the equations that Newton wrote down. If you know where they are and how fast they're moving at one moment, you can take these equations and propagate them forward, and they'll tell you where everything is going to be some distance into the future. Now, we know there's a variety of issues with that, but that was an extraordinarily powerful view. Now, if you imagine that everything is made out of atoms and molecules, and you want to take Newton's point of view, then in the same way that we understand that there are forces of gravity that affect the motions of the planets, we should understand the forces among the molecules, forces among the atoms, and we should write out Newton's equations for all of these atoms and molecules, and we should solve them. This is completely hopeless. And what the idea which appeared in the late 1800s was that instead of actually trying to solve these equations, we would imagine, so imagine all the molecules of gas in this room, instead of trying to follow every single molecule, let's instead ask questions. If I chose a molecule at random, what is the probability that I would see it moving at a certain velocity? Okay. Which somehow is a very different question than following the trajectories. And so, and actually how those two views are connected to each other is still not such an easy question to answer. And at the time, it was surely impossible. But they proceeded anyway. And so this is a shift then to this sort of probabilistic view. And one way of thinking about this probabilistic views is to say, well, look, whatever it is you're going to measure, I don't know, the positions and velocities of particular, let's measure the velocity of two different atoms. In the Newtonian view, I might have tried to understand exactly how these velocities were changing. Maybe one of them was positive and one of them was negative, and I don't know, they run into each other or something, and then they change places. But in this view, what you would say is, no, don't tell me about all those details. Tell me about the chances. You know, what might happen. And so instead, the output of this point of view might be, well, you know, what you'll find is that if you try many times, you'll see that the things you observe are being chosen at random, or seemingly at random, out of some range of possibilities. And so, in a certain sense, rather than trying to find the exact state of the system, atom by atom, molecule by molecule, what Boltzmann and Gibbs and others present us with is a view in which you should understand the range of possible states. So in the same way that when you go and roll dice, you don't predict, you apparently can't predict exactly what the roll will be, you do know that some rolls are more likely than others. Okay? And so that's the nature of the answer that you get. You get that there's some range of possibilities. And you can characterize that range of possibilities. But in the case of dice, you really can't do more. And in the case of the atoms and molecules in this room, the hypothesis of Boltzmann and Gibbs was that, well, maybe one could do more in principle, but in practice we can't. And so let's try to work in this picture. Now, there were a variety of reasons why people didn't believe this. It's worth remembering. I mean, now everybody knows the world's built out of atoms and molecules, so you might wonder why it was hard to reach that conclusion. If you work through the theory that Boltzmann and Gibbs gave us, and you ask, well, tell me about the atoms and molecules in this room, what you discover is that the typical molecule of oxygen is moving at 500 miles an hour. And so you might wonder why you haven't noticed. And the answer, of course, is you have noticed. The air exerts a pressure on you, and you know that this is different at different altitudes, for example, as there's more or less air above you. And that pressure is built out of the collisions of all of those molecules with you. And the pressure on the walls of this room are similarly built out of collisions of all the molecules with the walls. Now, the individual molecules are moving very fast, but they're also very light. And so the impact of one molecule is negligible, despite the fact that it runs into you at 500 miles an hour. But you can understand why people had a hard time believing this, which is important, because we sometimes look back on things that people. Well, this was legend has it this is what motivated Thomas Kuhn, right? So Kuhn, who wrote The Structure of Scientific Revolutions, was a teaching assistant in physics at Berkeley, and he found himself trying to understand why the Aristotelian view of mechanics held on for so long, because it was so obviously wrong. And he then started to realize, no, it's wrong, but it's not obviously wrong, right? A lot of our everyday experience is a lot more like what Aristotle described, in which objects don't move unless you push on them, than what Galileo said, which is that objects will keep moving even if you're not pushing on them. Right? It's a lot harder to actually create the situation in which Galileo was right. You have to get rid of all the friction and so on. Anyhow, be this as it may, okay, so since it was so difficult to convince people that it was right, you might ask, well, how do we know that it's right? And there's a variety of reasons. One is you calculate all sorts of things and you get them right. But maybe the most dramatic is that if it's really true that the pressure on the walls is the result of collisions of individual molecules with the walls, if I could look at a very, very small piece of the wall, presumably the number of collisions in that small piece is smaller. And if I could pump out 99.99% of the gas in the room, then presumably the collisions would be less frequent. And I might actually get to the point where if I could measure the force acting on the wall very, very precisely, I might actually be able to detect the effects of the individual molecular collisions. And that experiment, as I described it, is fairly hard, but there's one which is a little easier, which is, let me imagine taking a mirror, a very small mirror, and hanging it from a wire. And if I do that here, it won't move, because the collisions of the molecules with this side of the mirror balance the collisions of the molecules with this side of the mirror. So the force that the air is exerting on this side is the same as the force that the air is exerting on that side. But if I make the mirror very, very small, and I get rid of most of the gas, then the number of collisions is not so big. And if the molecules are actually moving at random, then by accident, right, they're being chosen out of their velocities are being chosen out of some probability distribution, then by accident it might happen that there are a few extra collisions on this side than on that side. On average, of course, they'll be the same number. But if there are a few extra collisions on this side, the mirror will tilt a little this way versus that way. And if I shine a laser beam onto the mirror and project it onto the wall over there, then even if it rotates a little bit, the laser beam will move a lot. And so I should be able to pick up these little tiny fluctuations, which are the leftovers of the individual molecular collisions. Okay? That experiment you can do, and that works. And there's another version of this, which is not hanging in air, but just a particle moving in a fluid. So if you look under a microscope at an object that you can just barely see under the microscope, you'll see that it's moving around. And that's called Brownian motion. And that's the result, again, the leftovers of the random molecular collisions. But what does this have to do with entropy? Well, in the simplest version of this, if you imagine that what is happening is that the system has a large number of possible states it could be in, and it's choosing that state at random, I could sort of count the number of states. So let me imagine that in this region of possible states, I can count the number of allowed states. And allowed here means allowed given all the constraints. So I have a gas and it's in a box, and the box is at a temperature and so on. And so obviously not all states are allowed, the gas is not allowed to come out of the box. But given what I can do, what I can see macroscopically, there's some number of ways of arranging all the microscopic states, all the states of the atoms and molecules that are consistent with that. And so let's call that number W. And
That's the number of states.
yeah, the number of states. And so there's this famous formula which is carved on Boltzmann's tombstone. Well, let me write it this way, which says that the entropy, which is the thing we knew about from thermodynamics, is actually the logarithm of this number of states up to a constant factor, which is a fundamental constant. We know it, right? Well, it's actually really a question about units. Never mind. So this is really bizarre, because what it's saying is that the entropy, which was a bookkeeping device for keeping track of heat flows, and as a result is very concrete, right? It says, heat moves from there to there, that happened at this temperature, so the entropy changed by this much, and stuff you can measure and stuff you can feel, right? Is related, in fact, is equal to this abstract thing which refers to the distribution out of which the state can be drawn. So somehow it's as if I told you that there's something that you can see about the roll of the dice which reflects not what happened on this roll, but reflects the distribution of possible rolls. So this is very odd, but it's also very tangible. And the reason is that you've all had the experience of taking a balloon and pushing on it and feeling the force as it pushes back on you. Okay? So you might ask, where is that force coming from? Well, you think, okay, if I lift this thing up, right, I have to apply a force. And those of you who've taken freshman physics, that means you're doing work, right, as you lift it up. And now the energy of this thing is higher, right? The potential energy is higher because it's higher up, and of course, if I drop it, gravity will pull it back down. So the forces are somehow related to energies. And that's this basic idea of mechanics. So let's go back to the balloon. I press on the balloon. I feel a force. I guess since I'm feeling a force and I'm moving against it, I guess I'm doing work just like lifting this thing, and the energy of something should have gone up. Except that, as many of you know, the part of this picture is that all the molecules are moving around at random, and their kinetic energy is related to their temperature. And if you do this right, and in particular if you're, do it standing in a swimming pool so that the whole thing's surrounded by water and nothing can change temperature because there's so much water around that's all at the same temperature. The gas inside the balloon doesn't heat up when you do this. And so actually the energy of the gas didn't go up. What happened was that because you constrained the volume by pushing it in, you've reduced the number of states that are accessible, and the entropy has gone down. And the force that you feel is related to that change in entropy. So it's not only true that this counting of the number of possible states gets related to heat flows, you literally can feel it, which is extremely surprising. Okay? By restricting the number of possible states of the system, you can feel a force. Okay? you reduce the volume, so the number of places the molecules can be is smaller. And in fact,
The velocities are kind of the same.
because the temperature is the same. In fact, the argument that you find in almost all textbooks, which very carefully calculates the pressure on the walls by imagining the molecules run into it and bounce off and carefully count the change in momentum and how much gets transferred, you don't need to do that. It's just that has nothing to do with it, actually. It's the change in the entropy. It turns out that those are guaranteed to give you the same answer, but that's a feature of classical mechanics. Doesn't that really have anything to do with what's going on? Yes?
The classical perspective doesn't infinite.
Ah, yes. Well, yes. There is a problem. So the point here is that since these are all continuous variables, when I say how many states are there in here, well, I don't know. If I decide to make boxes that are that big, I can count them. But why shouldn't I make boxes which are half the size, and then I'll get a bigger number? So this is true, and what that tells you is that if you stay within a classical world where everything's continuous, there's a question of where zero entropy is. Right? What corresponds to having only one allowed state? And that's not, if you stay entirely in classical physics, you don't know where that zero is. But that's okay, because you'll notice that all the things you observe, whether it's the force that you get when you change the volume, or the heat that flows, whatever, that's always related to a change in the entropy. And so where zero is cancels out when you compute the difference. Right, quantum mechanics tells us that in some sense there is a natural size to this box. And one way to solve the problem is to just take that natural size as the correct thing for the classical case. And that won't, of course, give you the right answer in cases where real quantum effects are important, but it will at least put the zero of the entropy in the right place. Okay? So this is all 19th century physics. But it is, as I hope you agree, getting weirder, right? We don't get to the weirdness of quantum mechanics and relativity, but there's something weird going on here. So now let's fast forward 50 years to 1948. And a fellow named Claude Shannon. Now Shannon, he did something really extraordinary. He created a field, which is a vital field to this day. But there's a remarkable fact that if you looked at a modern introduction to the field in a textbook, it would not look very different from the single two-part long paper that he wrote in 1948. So many people have created fields over the years. Seldom have they sort of hatched full grown, right? Where the thing that emerges in the first paper is still how we talk about it, almost in detail. We give the same examples. It's not that nobody's done anything in between and there aren't advances, but it's still true that if you want to understand this field, which is called information theory, you could go back and read Shannon's paper in 1948 and you'd be doing just fine. And by the way, the mathematics in that paper is relatively elementary. That is to say, it is not it's making very clever, sophisticated use of things that today many people learn in high school. Okay? It's not using something very esoteric. And many things happen in these papers. And I want to focus on one and then another, and then we'll see how things wrap up. So let me start.
What's the name of this field?
Information theory. And I'll try to indicate where, how many of the consequences of what he did. I want to start with something that he did in this paper, which is often not emphasized, but I think is really quite extraordinary. the field ends up being called information theory, and one of the things that Shannon tries to do, and does successfully, is he tries to make mathematically precise the intuitive idea of gaining information. So if you ask me a question and I tell you the answer, then colloquially you'd say you learned something or you gained information upon hearing the answer. You know, you're wondering how things turned out or how things are developing in this terrible shooting case in Florida. You pick up the newspaper and you see today, okay, I had a question in my mind. I read what's in the newspaper. I've gained information. What Shannon wanted to do was to ask whether there is a way of making that intuition mathematically precise. And so he set up the problem in the following way. You ask a question. And there's a set of possible answers. And let's do the simple case where we can just number them. 1, 2, 3, and so on. And, you know, when you ask a question, you not only have in mind a list of possible answers, you also know before you hear the answer that some of these answers are more likely than others. So if I ask you, what is the temperature going to be at noon tomorrow, there are more and less likely answers, right? And you could, for example, assign the odds on every one of these answers, a probability for every one of these answers by, let's say, looking at the history of April 20th of the last 30 years, or you could look at the data from some region over the last weeks or whatever, right? So you have a way of thinking about which answers are more likely than others. And so Shannon said, well, suppose that we really are precise about this. And so I can assign probabilities. And now what Shannon wanted to do was to say, when I hear the answer, you gain information, and he wants to assign a number, I, to how much information you gained.
What are the units of that?
Hang on. Right, that's right. So there's going to be a question of what units we measure it in, but that's an overall scale factor. So that'll appear at the end. And what he argued was that if there is a way of doing this, then it can't really refer to the details of the question and the answer. It can only refer to this setup, right? So these answers could be complicated things or they could be simple things. But in some way, if I ask you how much you learned, how much information did you gain, it has to do with sort of how many things you thought were possible and how sharply you zeroed in on the right answer. It doesn't have to do with exactly what you were asking about. And so in this setting, his argument was this information that you gain can only be a function of these probabilities. And he said, okay, well, what properties should this function have? And the first thing he said was, if all answers are equally likely, then the more possible answers there are, the more information you gain. So if you go into a situation and you know for sure there's only 2 possibilities, and someone tells you, yeah, it's the first one, or you go into a situation and say, well, no, there's 10 possibilities, and they're all equally good, and the guy says, it's the first one. You agree that in the second case you learned more because there were more possibilities. That doesn't seem very controversial. Second one, actually none of these are controversial. It's interesting. It's the consequence that's remarkable, right? So the second one is independent parts of the question should lead to additive information. So what this is saying is, if really the question has two parts that are independent of each other, then, and maybe that's not obvious from the way I phrased the question, but if I can decompose it in that way, then in some sense you gain a certain amount of information by hearing the answer to the first part, a certain amount of information by hearing the answer to the second part. They're independent of each other, so whatever this information is, they should just add up. And then he did a more sophisticated version of this one, of this idea, which is called branching. And I think the easiest way to do it is to just draw a picture. So imagine that you have a question, and the way you're going to, it's a complicated question. You want to know about something that's reasonably complicated. And so the way you're going to ask your question is to break it into parts that are not necessarily independent of each other, but have a structure. So that you start by asking some fairly general question, and then depending on the answer that you hear, you might ask a slightly different question. And maybe if you hear that it's the first thing, you ask a question that has 3 possible answers. You hear that it's the second thing, you ask one that has 2 possible answers, and so on. And getting to the real answer to your question is working your way down this tree all the way to the end. Now, you don't usually do things this way, but you know you can because you've played 20 questions, right? So, in fact, in 20 questions, at every node, at every branch point of the tree, there are exactly 2 branches that grow out, right? Yes and no. And getting to the thing you're trying to find is working your way all the way down the tree. And so what Shannon argued was, whatever this notion of gaining information by hearing the answer is, it must have the following property. That I can think about the information I gain on hearing the answer to my entire question, which is finding exactly where on which leaf of the tree I'm on. But I could also think at every branch point, I'm asking a question and I'm hearing an answer. And so I should ask, how much information did I gain when I hear these answers? But there's some probability that I went this way on the tree as opposed to that way. So the total amount of information I gain is the information I gain here, and then the information I gain here weighted by the probability I went this way, the information I gain here weighted by the probability I went that way, and so on, and add it all up, and that should give you the total amount of information. Again, this doesn't seem terribly controversial. The astonishing thing is that these conditions are sufficient to determine this function almost uniquely. And the only function which satisfies all these conditions, and this is the one. So for the less technically inclined, I think this is the only equation that I'm going to write down. It's that. And you'll notice that it has an arbitrary constant in it, and that's because nobody tells you what units to work in. So your units are up to you, and the convention in information theory is to say, well, this is really about asking questions and hearing answers, so what's the most elementary question? The most elementary question is one that just has a yes or no answer. So let's choose the unit of information to be the maximum amount of information I can gain by hearing the answer to a yes-no question. And that corresponds to setting that constant equal to 1 and making that logarithm to the base 2. And the resulting units have a fairly famous name. They're called bits. Now, if all of the answers were equally likely, so if we were actually in this regime, then in this case, you discover that the amount of information you gain is just the logarithm of the number of possible answers. So what does this mean? If there are 2 possible answers, you gain 1 bit. If there are 4 possible answers, you gain 2 bits, and so on. Okay. Now, what I didn't tell you when I was over here is that in detail, just like with rolling the dice, it's not quite true that there's a set of possibilities and you can count them. Some of them are more likely than others. And so if you're in a situation where some of the ways of arranging all the gas molecules in this room are more likely than others, then you don't just want to count them. You want to assign a probability to every single one of them. And Boltzmann taught us how to do that. And then if you ask, well, in that case, I guess this simple formula where you just take the count and take the logarithm, that's not going to work. So I somehow have to use these unequal probabilities. So how do I do that? It turns out that you sum over all the possible states, and if the probability of that state is p sub s, you take the probability times the logarithm of the probability with a minus sign. And so what that means is that the quantity which Shannon derived as being the only way of attaching a number to how much information you gain when you hear the answer to a question is exactly the entropy in what is usually referred to as statistical mechanics.
How did you get that second question?
Well, sorry, equal is the wrong, that was bad. So if all the states are equally likely, then there's a simple formula. If they're not equally likely, you have to do more work, and you discover that in order for this statistical description to correspond to the thermodynamic one, this is the quantity that you actually have to compute. Okay? Yes? Yes, right. So importantly, here, if you you can show, well, actually in both cases, of course, but here maybe it's we have an intuition for it, right? That if the different possible answers are not equally likely, you don't gain quite as much information. If you ask me a yes/no question, and you're already pretty sure the answer is yes, then when I tell you, you didn't learn quite as much as you did if you were really completely uncertain. And that's totally captured by this. Okay? And so this is actually always bigger than that for that reason. Well, or rather, it's always bigger than that because that's a mathematical identity that it's always bigger than that, but it captures this intuition about your information. Yes?
And even if it's yes or no, and we all think the answer is yes, but if you find a surprise and it's no, you still haven't learned any more than if you learned it was yes.
So that's interesting. Strictly speaking, this answers the question of how much information you gain on average. Okay? If we want to discuss how much information you gain from particular events, then you have to work a little harder. It's interesting if and actually the more natural setting there is the one where you don't really gain complete information. I mean, there's something a little weird about this, which is that you ask a question and somebody tells you exactly what the answer is. Would that this were actually true, right? What's usually happening is there's something you want to know about, and somebody tells you something, and it's kind of related to the thing you wanted to know about. And I'd really like to attach an amount of information I gained from that. And you can do that in a similar way, but it's a little more work, and so I wanted to leave it. Yes?
Well, can I think of the log 2 of PI as being the information if I get answer PI, then I'm averaging expected formula, I'm taking the expected information I gain from each of the answers? Or is that not?
That's roughly correct. The issue of the information gained from single observations is a little tricky. And as I say, if it's information about something, then it can be made untricky in an easy way. If it's just, it just, in this abstract setting, it's a little tough. If you go down to the case where you're learning about something else in particular, and you make that explicit, then more or less the argument you're making is correct. Yes. Okay. So it turns out that there's several things going on here. One is that
of course, thermodynamical assumptions.
Well, yes, of course, they're not they're related, right?
Yeah, exactly.
Well, but I think it's plausible that if you want, I think these are plausible assumptions in the context in which he was working, independent of our knowledge of thermodynamics. That is to say, I think these are reasonable statements about any mathematization of the concept of gaining information. The fact that
This is a physical realization of exactly that list of
correct,
assumptions.
but so let me. I'm not sure exactly what branching has to do with thermodynamics. I'm not saying it has nothing to do with it. I'm just saying it's not clear to me exactly what it has to do with it. So it seems to me that there's that this.
That is conditional probability. If you have basically if something is going to happen, conditioned on some, then it has to be.
Right, but why it should be the case, for example, that the thing which is going to turn out to be related to heat flows should obey this branching condition seems to me to be quite non-obvious. Okay, I'm not saying that. Evidently it does, right? Because they're related, but.
That's the causal probability link between the.
So we can discuss this more, but let me try to make the following point. I think that what's interesting is that Shannon set up the problem of making mathematically precise something that we do all the time, right? We exchange information. And he proved the theorem that the only way to do it that's consistent with reasonable assumptions is to compute a quantity which we already knew about from statistical mechanics, which is related to something in thermodynamics. Now we can discuss, whether maybe at the end of the day we should turn it all around and say that which one of these is the fundamental one. I don't want to do that. I want to show you that these different quantities all turn out to be the same. And before I'm done, I need to show you one more, which I think is the most surprising one. And so let me just do that now and then wrap up. So this part of what Shannon did is of very little technological consequence. The next part of what he did is of extraordinary technological consequence. And he said, how much space does it take to write down the answer? Okay? If you're going to ask a question and hear the answer, you'd like to write down the answer. How much space does it take to do that? Well, obviously, you have to agree on an alphabet. So let's agree on an alphabet. And the alphabet is that since we've decided to choose units in which the natural quantity is the answer to a yes-no question, let's choose a binary alphabet. Instead of choosing yes-no questions, we could have chosen something else, and we could choose another binary alphabet. There's an arbitrariness here, which is that constant that was floating out in front. But let's make consistent choices. So let's write down the answer in a binary alphabet. And then we have to be a little more precise about how much space does it take. What you mean is the minimum amount of space. And you also mean on average. Right? Because it might be that some answers take a lot of space to write down, and other answers take less space to write down. Okay? That's possible. So to be precise, let's ask about the average space per answer that I need. So imagine, for instance, you're going to ask a question that you can ask many times. What's the temperature going to be tomorrow at noon? You can ask that every day, and I want to write down all the answers. How much space is it going to take me? So the extraordinary theorem that Shannon proved is that the answer, so if you say L is the sort of code length that you need, right? You're going to write, remember, when you write down the answer, you don't have to write down the answer, you have to write down a unique pointer to the answer. So if you're an undergraduate and you're taking a course on Shakespeare, and I ask you, what are you reading this week? You do not need to write down the entire sonnet, right? What you need to do is, ideally, we have the same edition of Shakespeare's collected works on our shelves, and the sonnets are numbered. Tell me the number, and I'll go look up which sonnet it is. That's enough, right? So there's an abstraction here from hearing the answer to a question and writing it down to writing down something which, if we have some level of agreement, is a unique pointer to the answer. That's always enough. Okay? If I'm looking at a painting, right, there's a catalog of the collected works of the artist. Tell me which one it is. You don't have to show me the picture. Right? The remarkable thing is that the answer is the same. Now, this is surprising because you might have thought that if there are n possible answers, then in order to write down a unique pointer, I have to write down a number from 1 to n that can range from 1 to n. And so, so for example, if n is 4, then in a binary alphabet, I always need 2 numbers. Right? I need 2 binary digits in order to get to 4. Right? But this says, actually, that if for some reason some of the answers are more likely than others, you can in some way use that to shorten your code. So this is the promise, this theorem of Shannon's is the promise of an enterprise called data compression.
Do you want to multiply this by m capital?
No, sorry, code length per answer. The average code length per answer. So it says that on average, I can squeeze things down. So for instance, if I want to store images, right, I could say, well, in every pixel of the image, it could be black or white, and there's tens of thousands of pixels. So for every image, I need tens of thousands of bits that tell me black, white, black, white, black, white. But you know that if I just picked all those bits at random, I'd get something that doesn't look like any image you ever wanted to store. So apparently, some images, some combinations of these bits are more likely than others. In fact, some of them have probability almost 0. You could leave them out. And so by understanding the shape of that probability distribution, I should be able to store images in less and less space. Okay? And this, of course, is technologically incredibly important. And every one of you has used this because on your computer, there are programs that do this all the time. Sometimes without your knowing about it, and sometimes you actually call the program. So if any of you have ever zipped a file, this is what you're doing. Okay? And right, those of you who know to use compress in Unix, I don't need to tell you that this is what you're doing. It's the people who only use zip. You need to realize that this is what you're doing. Okay? And what's interesting is that it tells you that there is a shortest code, right? You can't go below this. And so that's interesting. It tells you that if you want to transmit a certain amount of information, there's a minimum amount of space that you need. And then it says, OK, so now there's a challenge. Can you squeeze everything down into that minimum space? So what's extraordinary here is that the same quantity appears as the answer to these very different kinds of questions. This is a question about writing things down. This is a question about how much you learn when you hear the answer. This is a question about, in some sense, the probability distribution of states taken on by a physical system. And this is a question about heat flows. The answers are all the same. So what does that mean? It means that if you were to do the following experiment, you measure the positions and velocities of all the atoms in this room. Okay, tough experiment to do, but we could imagine doing a small version of this. And now I want you to measure to some accuracy. So you measure the velocities to within a meter per second or something, and the positions to some, a micron. And now write down all those numbers and put them in a computer file. And now run your favorite compression program. If it's a good compression program, and actually for these kind of data, most compression programs are good compression programs. It's not terribly challenging. The file will get shorter, right? And then when you look, you'll notice that despite the fact that you typed lots of characters, the actual length of the file is much shorter than that. It's some number of kilobytes. Now take the room and warm it up by 10 degrees. Do the exercise again. You will discover that the file is longer. Well, why is it longer? Well, when you warm the room up, right, the molecules move around faster, so the range of velocities is broader. So the range of states that take on non-zero probabilities is larger. But since this is the same as that, what it means is that if you count how many more kilobytes you needed on your disk to store the data, then except for all these pesky constant factors that I've conveniently ignored, you actually know how much heat you had to put into the room in order to warm it up by 10 degrees. And so this very abstract thing that has to do with how much space it takes on your disk to store a bunch of numbers is directly related. And as I say, except for units, they're actually equal. Okay? There's a conversion from kilobytes to kilocalories, okay, if you must. I would have said joules first, but I thought it's a general audience. There's a direct conversion from bytes on your computer to calories of heat that you put into the room. Okay? And so these ideas that emerged 100 years apart, since they're the same mathematically, and it's not an analogy, it's an identity, it means that this very abstract idea about data compression and this very concrete idea about heat flows are related to each other. And so I hope that this gives you a sense for why I think that entropy is a sort of underappreciated example of the power of mathematics to unify our understanding of the world. Thank you.
For one or two questions.
When you're talking about code length and storing information, I have this sense that if you don't compress information, it doesn't take the computer much work. But if you want to compress information and then manipulate it, then it takes the computer longer to do things. And I'm wondering if that idea is related to your balloon example about force and doing work and feeling pressure.
I don't see it directly related. What I would point out is that when you compress data, one of the things that happens is that the data, after it's compressed, looks more random than it did before it was compressed. Right? Remember I said that the way you achieve the compression is that you either implicitly or explicitly exploit the fact that different things have different probabilities. If it wasn't for that, you couldn't compress anything. So what you're moving toward, in order to do the compression, you have to make all of the possible things that you write down be almost equally likely, which means that it's totally unstructured. Okay? So you could say that the reason it's more difficult to do anything with the compressed data is because you squeeze all the structure out of it. And most of what you want to do is about the structure. So in some sense, you have to sort of look up what your code book was, which is in some sense where all the structure is stored, and put it back in order to extract anything that you actually care about.
I'm not sure if this is a question you asked, but I didn't quite get the answer. So you said in the case where the probabilities are absolutely equal, that this is sort of the maximum information gain. And when the probabilities are less equal, then you get less information. But it's true that if something is very more likely than not, then to find out it's true is not so much information. But
Yes.
the opposite case, when something would seem to be very unlikely and then it turns out to be true, you'd seem to have gained more information. Right?
So if you, so let me answer first not the question you asked, but the one that maps from here to here. So what is true? So somebody asked this about, the technical question, can I think of this as being, this is the amount of information I gain from every answer, and now I'm averaging, so I sum over these probabilities. In terms of code length, that's exactly true. That is to say, it is, if you try to make the shortest possible code, you will always take more space to write down surprising things than unsurprising things. That's the way you achieve this. So it's certainly true that if you're thinking in terms of just writing stuff down, you need more space to write down the things that you heard that were surprising than the ones that were unsurprising. So that's interesting. Okay. In terms of how much you learn, again, you have to be a little careful in asking information about what. And the reason is that so in this setting, it's really simple. It's information about which possibility it was. But that isn't really so natural. So you usually are interested in information about something. And then, actually, it's even more flexible than saying some things you gain more information than others. Actually, from one observation, it's perfectly possible that you lose information. And I think we've all had this experience. Everyone who's been through school knows that they have occasionally asked a question, and after they hear the answer, they're sure they know less than before they asked. Okay. What is true, of course, is that on average, that can't be true. Okay? It must be that if you keep asking questions, you are, on average, gaining information. But on any one of them, there's absolutely no guarantee. And in fact, it's sort of it is a non-trivial property of the entropy that these are both, that these can coexist, right? That you're guaranteed that on average you gain information even though you're not. Barry.
Is there a quantum mechanical analog in information theory to the quantum mechanics of replacing probabilities by density matrices?
So of course there's a large subject called quantum information theory, and I know less about it than I should. It's certainly the case that, as you know well, the natural generalizations of entropy and so on are all related to the density matrix rather than probability distributions. What I don't have a facile answer for is whether is how one takes these coding questions into the context of mixed states where the difference between a density matrix and its diagonal elements become important. And I just don't know the answer to that.
That was exactly my question.
Right. So I don't know is the correct answer. Well, that's always a good place to stop.
Let's thank the speaker.